Hello students, this is Dr. B and we are doing the flood module in Concord Consortium. We're on activity 3, permeability problems, and we're going to start out on page 1, of course. In this activity, we'll use models to explore how permeability affects flooding. We'll compare flood risks and impacts in areas with different kinds of land cover, rural, suburban, and urban, and observe differences in the timing and extent of flooding during heavy rainfall. So let's get started. More people at risk. In the last activity, you learned that some areas of the United States are more likely to experience flooding than they have in the past. You might think people would move far from rivers to avoid the risk of flood damages, but the opposite has been true. Rivers have always been an important part of the transportation system in the United States, and therefore a place where people can more easily find jobs and raise families. The photos below show Kansas City, Missouri during 2 different time periods. Look at both pictures and then answer the questions. So here's Kansas City in 1869. It's not a photograph, it's just a drawing. It shows pretty sparsely populated. They do have roads, they're not paved. There's some houses, but not that many, and which is really different than the densely populated area here of Kansas City in 2007. So what are some of the differences that you notice about Kansas City now as compared to the past? Check all that apply, and then you can check your answer. So you get to do this one on your own. There are more buildings along the river. There are more people living and working along the river. There's less natural space undeveloped near the river. How do you think the additional buildings and roads near the river have changed flooding in the city? Consider both the likelihood of flooding and the damages to the people living in the city. So here in 1869, we don't see a whole lot of buildings along the river here. Here, we don't see anything super close to the river, but there are things fairly close to the river here in the 2007 photo. In this more populated Kansas City of 2007, we notice a lot more pavement. There are a lot more houses and buildings and businesses, so there need to be more roads. Roads, we've talked about, are impermeable. Water does not soak into the pavement. So pavement decreases permeability. The water does not soak into the ground when it hits pavement, so it runs off into the river. Let me show you how that works. So let's say this is a river basin. We'll put that down here. This is where the water is going to end up eventually. But here's the water to begin with. And here's a permeable surface. This is a towel. We'll say it's grass over dirt. And this absorbs water really well. So I'm going to take some water from this pitcher, we'll pretend it's rain, and pour it onto what's going to stand in for grass over dirt. I'm just going to pour this on the towel, and as long as the topography is right, it's going to soak in. It's not going to run off. We can see that it'll just soak right up. Maybe it'll make a puddle or two for a while, but it's going to soak in. Now, if this topography tends to be a little bit steep, that water is going to stay in the soil and it's not going to run into the river. So this is a permeable surface. In real life, next to rivers, this is grass, this is parks, this is farm fields, anything that's going to absorb water, anything that has plants and soil, plants over soil. We're going to get rid of this here, and we're going to put an impermeable surface here. This is a road, or cement, or a parking lot, or your roof. Anything that is impermeable or doesn't absorb water. I'm going to pour about the same amount of water onto this impermeable surface, and you can see eventually it's going to run right off that surface. It's not going to soak in. We'll have some more rain here. And if this surface is tilted at all, it's going to flow into the river. All of that water that fell on pavement or your roof or a sidewalk or a parking lot is going to flow into the river. And so the more pavement we have, the more water we're going to get in the river. The more impermeable surfaces we have, like roads or roofs or sidewalks or parking lots, the more water that's going to just run right off those impermeable surfaces and into our rivers and lakes and streams. So hopefully that demonstration helped you learn that impermeable surfaces in cities, like roads, like sidewalks, like roofs, like parking lots, don't absorb water and that water runs right off. These are impermeable surfaces. Permeable surfaces act like towels. They just soak up the water and don't let it run off into rivers or streams or lakes. And they help keep our rivers and streams and lakes cleaner and less flooded. So, as you saw on the last page, the population of Kansas City grew over time. As more people moved in, they developed more areas. Farmlands and forests became neighborhoods with houses, schools, roads, and other buildings. So, houses, schools, roads, and other buildings are like this part of this simulation. That's like the roads. The towel part is like grass, parks, your lawn, hopefully, your garden, farm fields, all of that. I'm going to get it raining here, and you can watch what happens as we follow two different water droplets. One's just going to kind of soak in. It'll take a little bit of a pinball action as it goes into the soil. We can get it to, we'll wait till it rains some more. We can see that the water here, it's either running off into the permeable area or it's running off into the river here. We can see that the water table here is starting to kind of fill up or climb up or get higher as the soil absorbs more rain. You don't have to dig down quite as far to reach water. Here, under the pavement or the impermeable surfaces, you can see that the water table is different because it's not absorbing any water from the surface here. As more rain runs off the pavement into the river on this side, this river gets higher. Let's follow another water droplet here. Those are going right in. Let's see if we can, we'll wait till it rains again here. We'll turn up the rain a little bit. As people build in the area, they cover the parts of land with pavement, buildings, and houses. Building on the land makes it difficult, if not impossible, for the rainwater to pass into the ground. Scientists call this the permeability of the surfaces. You can see this rain's going to land, and I guess that one's going to soak in. Permeability is one of the 4 factors in the flood diamond. Remember, the flood diamond is topography, starting water level or water table. You can see that right here. You can see it's easier for this river to flood if the water table is up here rather than down here. The water table over here, well, the river level anyways, is pretty high compared to this one. You can see that water run right off over to the permeable side, or some of it's running over here into the river. Droplets that fall over here always soak in. Let's see if we can follow another one. That one just is going to go right in the river. Using this model, you'll investigate how rainwater moves when it lands on different surfaces. Here we go. Here, it ran right off the impermeable surface to the permeable surface. I'm going to stop that here. The green surface represents a field or a farm, like the towel in our model. It's going to soak up the water. The water is going to go right through the plants into the soil and just stay in the soil until it gets to the water table, and the water table will eventually rise as the soil absorbs more water. The black surface represents a paved area, like a parking lot or a road or sidewalk or your roof. Run the model and follow several water droplets. clicking on the follow water droplet. We already did that. Will help you observe how the droplets move on and below two different surfaces. You can grab a snapshot here. And I've already drawn on this one. You can see that the arrows are coming down and showing that the water goes into the water table here. We can maybe add to this drawing and show that this is going right into the water table here. This water is hitting the pavement and then it's running right off into the river, or some of it might hit the pavement and run off into the permeable area, but it's definitely not being absorbed. There's no water being absorbed by the soil under the impermeable surface. The parking lot, the road, the sidewalk, your house. Because roofs are impermeable, unless of course you've got a green roof, unless you're growing plants on your roof that soak up the water, but not many of us do. There are a few green buildings in our neighborhood that do this. The Target Center in Minneapolis is the basketball place and has a green roof, lots of plants growing on top. Remember, a high permeability surface allows water to move through it quickly. A low permeability surface slows down the movement of water through it. From a model run, which surface do you think is less permeable? Farmland or paved area? This would represent farmland. This side would represent a paved area here under the black. Using the snapshot from question 5, explain how rain moves when it falls on a paved area, such as compared to a farm. So here's the farm, here's the paved area. We made a word bank in class. We use the words through, less permeable, rain, river, pavement, and to represent permeable, we put farm, field, park, grass, forest, rain garden, and floods. This is a word bank you can build your answer from. This is not the answer. Question 6, how certain are you that the evidence from the model applies to permeability of surfaces in the real world? Well, I'm pretty certain, and I'll show you why. You might have seen one in these neighborhoods, in your neighborhood. Water flows down next to the curb in the gutter and flows into the storm sewer, and then it flows from the storm sewer into a lake or a river nearby. In some places in my neighborhood, spray painted next to the storm drain, it's a reminder to don't pollute, don't pour your oil or paint or toxic chemicals down the storm sewer because it goes to a lake in our neighborhood. In some neighborhoods, it might go to a river. This is a rain garden, and a rain garden is an effort in our city to stop water from going down those storm sewers and getting to the river or lake and flooding it. What we want to do is the water to come down the curb, enter here into the rain garden, drop the sediment, the mud, the soil right here, and then flow into the rain garden, water the rain garden, water those plants, and soak right into the soil. So we don't flood our lake. Here's a closer view. Instead of a storm drain right here, the water flows into here and fills up this rain garden. I've maybe seen the rain garden full 1 or 2 days a year. It makes a little bit of a puddle, but the plants are native plants with very deep roots that help the water soak into the soil very quickly. The water just kind of follows the path of the roots and soaks in very quickly. And I know since my community is making major efforts to have water from impermeable surfaces go to permeable surfaces and soak in, I know this is a problem, and I know that flooding is something that my city is thinking about. So I'm pretty sure this is the model that we used is a pretty good model. So I wrote, I'm pretty darn certain this is a problem because I've seen water flowing into the storm drains that rain falls onto the street and then goes into the storm drain, goes down the gutter and into the storm drain. I've also seen what the city is doing to manage stormwater by running it off pavement into permeable areas, into rain gardens. Permeability. So far in this model, you've used Flood Explorer to investigate flooding in Silverton. Now you'll use a more current map of the same area, Silver City. More people have moved in. There's still farms and parks, but there are also city areas and suburban areas. Below you can compare the old Silver City map with how it looks today. So let's take a look at these two maps up close. So the older map shows a lot of green areas. Silverton is a very small town with maybe just a general store and a few other stores. If we go over here and look more closely at Silver City, we see, comparing it to Silverton, there's a lot more roads. We see a hospital. You can see a lot more development here. You can see these little rectangles here that show there are city blocks here where people are living. You can see the same thing in Brookside. If we look at Brookside here, it looks pretty urban. There's a lot of pavement. And if we go over to Brookside on the older map, there is no Brookside. It's all just fields or forest here. So let's shrink this map down and go back to looking at our questions here. I took a snapshot of the new Silver City map and he circled the areas that have changed the most. We can do that together here. So here's the city. Here's the most current map on the right, and I circled the areas that have become much more urban and look less green, have more pavement, have more of those rectangles that represent city blocks, to show that there are less permeable areas here in these three parts of the map, and they have changed from the parts of the map in the older version of the map. So describe the changes that you circled in your snapshot. There's a great deal more pavement in Silver City on the right than Silverton on the left. So I compared Silver City and Silverton. There are a couple other areas here. There's South Side, there's also Brookside. You can write about the changes in Brookside and South Side on your own. Which map, past or present, has more impermeable surfaces? Well, my class all voted for the current map of Silver City having more impermeable surfaces. Here and here and here. We made a word bank. Would the likelihood of flooding increase as a result of the development of urban areas in Silver City? Why or why not? Well, we made a word bank that said more runoff, more pavement, more impermeable surfaces, like roofs and parking lots and sidewalks. That's going to lead to more flooding. And we gave a definition or some examples here of impermeable surfaces, surfaces that don't absorb water. So you can construct your response using this word bank. You don't have to use all of the words, but this gives you a good idea of the types of words that should be in your answer. Here's a reminder of the flood diamond. Its precipitation, permeability, how much water goes through or is absorbed by a surface, the water table, how far you have to dig down to hit water, and topography, the shape of the land. Is it a hill, a mountain, or is it really flat? Over the last 100 years, the areas surrounding Silverton have become urbanized. More people moved in, and more homes and buildings for businesses were built in the area. Silverton became Silver City, and there are still farms and parks in Silver City, but there are also city areas and suburban areas. Using the Flood Explorer, you'll compare flooding events between Silverton and Silver City under the same rain conditions. First, look at the snapshot below. It shows a large flood in Silverton when the amount of rain was heavy. The storm duration was long, and the starting water level was high. So let's go look at the snapshot. It's a large flood. Now run the Flood Explorer for Silver City under the same conditions. Set the amount of rain to heavy, the storm duration to long, and the starting water level to high. Use observations from the map and from the graph to support your answers in the questions below. So this is a snapshot. It shows us Silver City when it was Silverton, older situation. There was a little bit of flooding. It was about 1,500 acres for, like, let's see, 4.5 minus 2 is about 2.5 days. Let's do the same flooding with our new map of Silver City, not Silverton. So we set the amount of rain to heavy, the storm duration to long, the starting water level to high, and then we'll let it rain and we'll watch the graph. We've gotten to 1,500. Oh, here's where the last flood ended here in the snapshot above. It went to about 1,500. And here's about, this flood went to about 1,800. We can look at gauge 1. It was above flood stage at the undeveloped area. We can look at gauge 2. It went above flood stage just a little bit. There's just a little bit of blue above the purple. And at gauge 3, it flooded the town just a little bit. Okay, let's go answer our questions. Based on the model run for Silver City and Silverton, which time would the people be at greater risk of flood damage? People living at Silverton in the past, people living in Silver City now, same risk at both times, no risk at all in both times. Well, here's Silver City. This is flood gauge 3 here. And you can see it flooded the town a little bit. The peak here on the graph was 1,800. That's above the peak of 1,500 here in Silverton. Compare the acres flooded versus time graphs for Silverton and Silver City now. How does the number of acres flooded change between the two? More areas flooded, less areas flooded than the past. Flooded areas remain the same, no areas flooded now and in the past. Well, we can see there's a little bit of flooding here, there's a little bit of flooding here, around here, down here by the airport. If we go up to the other map here, it doesn't look like there was any flooding. Can you go to the gauges? Nope. Can't look at the gauges. The acres flooded were about 300 acres different. So we know that there's a little bit of difference in terms of there's 1,800 for new Silver City, the new map, and there's only about 1,500 on the old map. You can look at those too. And then you can answer question 13. Based on the model run for Silver City and Silverton, during which time would people be at a greater risk of flood damage? Well, if there's more acres flooded, that would probably mean more flood damage. So which model, old or new, has more acres flooded? Check your graphs if you don't remember. Explain your answer to the previous question. Consider both changes in the likelihood of flooding and the people and properties resulting from urbanization. So if we look at this new, more urban map, we've got buildings pretty close to the river here, in West Silver City, in Silver City, in Brookside, in Southside. So there's some neighborhoods right up next to the river. So if the river floods here in this second scenario, which it did, it went up to 1,800 acres flooded, it's more likely to cover some of these neighborhoods that are right next to the river, because there are more people living next to the river. So some things you can use as a word bank. You can say the number of acres flooded. You can talk about houses near the river. To be specific, the number of houses near the river. The more houses near the river, the more houses that are going to be flooded and the more property damage you're going to have. You can talk about permeable and impermeable surfaces as well. How certain are you that the people living in the time period you chose in question 14 so perhaps we want to pick people living in Silver City now. Why are you certain or uncertain about the greater risk, the time period of you chose? Well, if you understand how cities work, and you understand the difference between permeable and impermeable surfaces, you know that water falling on a road is going to run off and either get soaked up by a permeable surface or run straight off to a river or a lake and perhaps flood it. You know water's falling on a farm field or some other kind of impermeable surface or permeable surface, it's just going to soak up. Because permeable surfaces work like a towel or a sponge, and they soak up water. So it doesn't run off to a river, a lake, or a stream. So based on your certainty of how permeability works, you can use that to shape your answer. So you can use how permeability works. And you can use how your city plans for impermeable surface runoff, or in other words, storm runoff, for your certainty. During the flood in Silver City, what happens along Route 8 shown in the bottom right-hand corner of the map? How does this affect people throughout the whole Silver City region? Well, let's see, Route 8 is right here. Let's back this up so we can get the maximum flooding here. So I've gone to the graph where it just peaks out at 1800. We can see that Route 8 is a little bit flooded here. It looks like there's a lot of water over the road right here where Route 8 goes right next to the river. So that can help shape your answer to question number 18. If the road is flooded and you can't drive on it and maybe the bridge is underwater, what do you have to do? Can you still drive on that road, or do you need to figure out a different way to work in the morning? Might you have to take a big detour? This is the first half of Activity 3. We'll do the second half in another video. Thanks so much for watching. This is Dr. B signing off on the first half of Activity 3 in the Concord Flood Module. We're leaving off on page 4. See you in part 2.